המסר ברור, צריך שיהיה פה גונג. לא, אני לפני אחד יותר איתו.
חשבתי שהוא כתב, המסר ברור.
לא, הרצאה היא למת. לא יכול להיות מגניב.
לא, צריך לראות את זה ברמפון.
זה היה טוב.
Hi, I'm going to talk about bounded cohomology, something I heard in Switzerland from Mark Vogel. He was talking about higher type model theory, which is the study of representations of surface groups into general semi-simple groups. One of the main tools there was bounded cohomology. He talked about it like 20 minutes, but I got really enthusiastic about it for some reason. And in the next hour and a half, I'm hoping to share this enthusiasm with you. And so let me mention some things that we're going to see, perhaps not with a lot of details, but how bounded cohomology can be used to say a lot of things in different areas that people like. So the first thing would be quasimorphisms or almost homomorphisms that we saw with moving, and actions on S1. Strongly proximal actions, like we saw with Yair in a nice paper by Burger from 2007. We'll see some word problems and commutant domain that we saw with Dai. And finally, some relation to non-positively curved manifolds, geometry, Homo hyperbolic manifold groups. So let's start with some definitions. The first hour will be pretty dull. We're going to compute some cohomology groups, see a few definitions, and then later I hope to see some cool stuff that we can do with this. So let's start with some history. Bounded cohomology was first defined by Traube and Johnson in the 70s in the context of Banach algebras, but the first important use of it as an independent field is by Cohomology from 1982 in a paper called Volume and Bounded Cohomology, where he defines a really cool term called the simplicial volume and relates it to bounded cohomology. What's very cool about it is that it's a homotopy invariant which encodes some non-trivial information about the volume of certain manifolds and their topology. So let's start by definitions. Gamma will be a discrete group most of the times. And A is some abelian group. Mostly A would be R or C. And we define the complex C and gamma A to be functions from gamma to the n plus 1 to A. And we have a co-boundary operator, delta F, which sends delta is from Cn to Cn plus 1. So here we have a function of n plus 1 variables, and we want it, and then we want delta F to have n plus 2 variables. So we have this alternating sum. Where we omit the I coordinate this time. And so a standard exercise is that delta squared is equal to 0. And when we have that, we have what's called a chain complex. We have these. We have that the composition of delta twice is 0, and so we can define the homology proofs of such things, of chain complexes, as the image of delta, sorry, the kernel of delta here modulo the image of it here, so h, in this case, n plus 1. Be the image of delta. So elements in the kernel we call cycles, and elements in the image we call co-boundary. And these groups measure how much this sequence is non-exact. And how we define it here, it turns out that this chain is exact. So we have to, and object homology groups are going to be trivial, so we have to do something a bit different and define Cn of gamma A of gamma, which is object gamma invariant functions. So we have an action of gamma Cn gamma A by gamma by this diagonal action on the functions here. And so we say that f is invariant if gamma f equals f for all gamma.
Could you say a word maybe why does it vanish? Why does the cohomology vanish if you define it in the first way?
I can just give you a concrete, give me a function, and I have a way to produce a function in the previous chain, which is a co-boundary.
But in a more meaningful way? Like I'm sure it's an exercise that could be done.
In slightly more conceptual way, maybe. Before you take gamma invariance, you ask?
Yeah.
So it's nothing to do with the group structure of gamma, right? So you can just put there a set. If it was a finite set, if you think of it, this is just the
Singular cohomology.
simplicial homology of a simplex, which is contractible.
Yeah.
If it is not, if it's infinite, then basically it's the same.
Except for the zeroth, I guess. Probably the zeroth will have the...
Okay, the zeroth.
Yeah, okay.
So we're going to talk about gamma invariant functions on gamma to the n plus 1, and later I will show that we can restrict the functions on gamma to the n, but then the co-boundary operator is going to be quite uglier. And the nice thing about this is that this is the same as taking a singular cohomology of the KG1 for a group. So we have K gamma 1, which is a topological space with fundamental group gamma and every other homotopy group 0. And we get that H of n gamma A, as we defined it earlier, is the same as H n of x A. Well, this can be computed as singular cohomology.
Maybe we'll just say a word about K gamma 1. For those who haven't seen this before, for every group gamma, as Raz says, there is one can construct a space which has a connected space which has this group as pi 1 and all the higher homotopy groups vanishing. And one can do it by taking a point, gluing edges for generators, putting cells for relations, etc., etc. And it is a fact. I mean, in fact, one can construct many such spaces with this property, but the fact is that they are all homotopically equivalent. And this unique up to homotopy class is called K gamma 1. The Eilenberg-MacLane space.
And this is true for any A? If A has torsion or something? It's a bit just maybe it's true.
I think it is.
If any.
So now when we have this, we can add B everywhere. So we're going to define Cn gamma B as all functions from gamma to the n plus 1 to A, which are bounded. So we're assuming A has some norm or anything we can say about boundedness. And so we have every bounded function of gamma n plus 1 is of course a function of n on gamma to the n plus 1. And this observation that we can compare bounded functions to non-bounded functions is going to be very crucial later. So this inclusion of complexes gives rise to a function from the bounded cohomology to the regular cohomology of the group, which is called the comparison map, the nth comparison map. And it is not in general injective or subjective, but this, but sometimes we can identify types of groups by properties of these maps. So let's start computing some cohomology groups. So one important remark, which I'm going to use sometimes, whenever it's more comfortable, is that if we know if f is gamma invariant, then I know f by knowing what it does to these types of things, because I can multiply it by gamma from the left, and so we can define Cn. Sometimes you multiply it by that, by just functions from gamma to the n to A. But this time the co-boundary operator, if we want the homology or cohomology of these types of chain complexes to be the same, then the co-boundary operator is going to be a little messier. It looks like this. So this looks quite scary, but we won't have to check that functions are gamma invariant.
So on the sigma, it's mu I times mu I plus 1?
Yes.
So again, let me repeat this because it's crucial if you haven't seen this. If we look at functions from gamma to the n plus 1 to a, which are gamma invariant, we can identify it with functions from gamma to the n to a, and we have the boundary operator b for the other complex, called the homogeneous complex usually, and we just put it back to that new complex called the bar resolution complex, and get a new one, and we can compute what d bar will be, and this is the formula. It's very standard.
And we can even do the like chain complex morphisms.
So by construction it gives the same homology as before.
So if f was gamma invariant, we can send to the following function on n variables. Just a value f of 1. And on the other hand, we can take h, which is not gamma invariant, but an n variable, to the following function. So we're multiplying on the left each coordinate with the previous one inverse, and then if we have gamma times gamma, like the diagonal action, then we see that the new gamma 1 has a gamma in front, and so it will cancel, and this is a gamma invariant function on n plus 1 variables. So once we have these two things, and an important remark here is that if we take the classifying space of gamma and we look at bounded cohomology, then in isomorph situations we don't need all the other homotopy groups to vanish, and for Gromov showed it in his paper that the bounded cohomology of CW complex is determined by its bounded cohomology of the fundamental group. So we can use it in uglier spaces or things that we can compute easier just with the So let's start with the zero cohomology. And we're going to use the bar resolution. These are the functions from gamma to 0 to a, which is just a. And when we look at b of element a, we get that it's just h minus h. So every element here is a cocycle, and so we get that h. And this is of course also true for bounded cohomology because constants functions are bounded.
Can you say again what does the bar stand for? We have b for the bounded, and then the bar is what?
Is for looking at functions from gamma to the n to a.
Rather than n plus 1 and
and gamma
and
invariant.
invariant.
Now we have the first place where bounded cohomology and regular cohomology differ. We have k. We saw that the map from C0 C1 is the zero mod. Everything here is got to 0. So we have no co-boundaries here. So we only have to find which elements here are sent via delta to 0. And the very nice thing is that if we have a function here and we look at d there, we get the d of h, which is now a function of 2 variables. It's h of gamma 1 plus h of gamma 2 minus h of gamma 1 times gamma 2, which is exactly the relation that we want from homomorphisms. So if this is 0, we get that h was a homomorphism, and we don't have any co-boundaries, and so the regular cohomology, first cohomology of the group, is just the homomorphisms from gamma to a. But now if we take a to be r or z, then we don't have any bounded homomorphisms to r or z, and so the first bounded cohomology of the group, when we take let's say not S1 or a trivial normed space, then we get that the first bounded cohomology is 0. And now we get to the first really cool one, which is the second bounded cohomology. And the most important thing here is going to be the comparison line. We're going to work with R, but just a bit easier. But it works everywhere. And we're gonna define again what a quasimorphism is, or almost homomorphism. So these are quasimorphisms of gamma, which are functions from gamma to R, such that this homomorphism relation is bounded. So if this is 0, then f is a homomorphism, and if it's bounded, we call it a quasimorphism, as we saw in Forward's talk. I mean, he defines that it takes finite sets of values, but here we're going to talk just about bounded quasimorphisms. And the proposition now is the following: that the kernel of this comparison map, all elements of the bounded second cohomology, which are sent to 0 into regular cohomology, which is isomorphic to the quasimorphisms on gamma modulo the trivial quasimorphisms, which are homomorphisms plus bounded functions. So the kernel of the comparison map measures how many non-trivial quasimorphisms we have. So let's prove that. We're going to define a map from quasimorphism of gamma to the kernel of C2. Which takes the quasimorphisms and send it to the class of d squared of f just the co-boundary operator from C1 to C2. And first we'll show that this is surjective. So what are elements of the kernel of this map? These are elements of the bounded cohomology, which when I look at them in the regular cohomology, they become co-boundaries. So there is a function where when I do the co-boundary operator D, I get that it's bounded. But it was not a co-boundary in HB of 2 necessarily. So let's write it down. So what is an element of the kernel? Means we have means that we have some function f that alpha is the co-boundary of f. But alpha was bounded because it's in the kernel. And we already saw what d squared is what some people call the defect of f, which is how far is f from being the homomorphism. So this means that it's not d square, it's
The second,
yes.
I mean, this will like 0.
So being in the kernel of C2 means that we are the boundary of some function, and this function has this property, which means f was a quasimorphism. And so this map is well defined and it's onto, and now we can get the kernel of this.
We don't assume f is bounded, right?
It's not bounded. I mean, it might be bounded. But alpha is bounded.
If f was bounded, then alpha was 0 in
And then you have it in
cohomology.
plus. So why do you have plus at infinity? Just
It's bounded functions.
right, but it doesn't go automatically into 0. Oh, okay, yeah.
But
Okay. You're proving that it goes.
Inside of
He showed now that this map d bar is surjective and now is about to compute its kernel.
Yes.
There you will see the infinity.
And of course, infinity is.
So this is a bit confusing because we're comparing the kernel of the map to the kernel of another map, and it took me some time. But remember that the kernel here is just a subspace of the bounded cohomology of gamma of A, so we just need to see which functions are 0 in the second bounded cohomology. So we have that this is 0 in bounded cohomology, which means that it's a co-boundary of some bounded functions. So, and f is a quasimorphism. So d of f is equal to d of g, where g is bounded. But that just means d of f minus g is 0. It's easy to check that d is linear. And so if we and we saw that d measures how far we are from being a homomorphism, so this means that f minus g is a homomorphism. So if we write f as f minus g plus g, and g is bounded, then we get that f is a homomorphism plus a bounded function. So this is exactly the kernel of this map. Good.
Can you explain again the surjectivity?
Yes. We want to see what are elements of this kernel. So this was the comparison map. So So being in the kernel means that when we take a bounded cohomology class and we view it as a cohomology class of non-bounded functions, it becomes 0. So alpha is d of some function. But when we write this down and we know that alpha was bounded, then we know that f satisfies exactly this relation. So f was a quasimorphism. And so every element of the kernel comes from d of some quasimorphism.
I didn't follow. Maybe you can go through again the relation between like the boundary map and being the homomorphism and being the quasimorphism.
Yep, so D2, which sends functions on one variable to two variables, is exactly this, just this. When you say that d of f is 0, it means that f is a homomorphism. When we look at elements here, C2 is exactly taking a class and viewing it as a class in a regular cohomology. So if alpha is here, then when I view alpha as an element of the regular cohomology, being 0 means that you're at the boundary. It means that you're d of something else, of a function. But writing again d of f, you get this. But we remember that alpha was bounded. So this relation just said that f is a quasimorphism.
This relates to what you said in the beginning, that the regular cohomology is always 0. No?
It's because the boundary map in both complexes is the same boundary. This is it may seem different because you define it on less variables, but because it's the same boundary map, this is right.
I'm not sure, but maybe correct.
Okay.
So you divide by the images which are bounded after d has been applied to them. It's not like you only take bounded function and apply d to them, right? Okay, that's good.
Can you give an example of a quasimorphism which is not a sum of homomorphism and something bounded? It's just, it seems like
We gave this example 2 weeks ago.
No, but the example in your case it was that all such was really להגיע למטה and then it's really a homomorphism plus constant, not a constant but something
the examples
bounded.
I gave are not
of this kind.
qualified here. Well, are you going to give an example?
Yes.
Okay.
You will. If you don't mention the Brooks example, the Brooks exercise, you will. I mean, maybe I suggest that you will give it before the break, and people could think about proving it during the break.
So, yeah, that's exactly what I'm going to do. Once we have this relation between the kernel of the comparison map and quasimorphism, then in some cases we can compute exactly what is the second cohomology, bounded cohomology group, and see how it differs from regular cohomology. So now I'm a bit confused about my first example, so hopefully we can close that. Notice that everything here works if we replace R by some other thing, but then this might be just a sum and not a direct sum. And so we take gamma to be A to be Z.
In case of torsion, you mean, or? I mean, if for Z it would be...
If we take S1,
Okay. Oh, okay.
So I'm going to use the description of the regular second cohomology group as classes of isomorphisms of central extensions of the group gamma by K. So that. So central extensions are exact sequences. And with these, such that the image of A is inside the center of gamma hat. So the second cohomology, regular cohomology of the group, matters in how many ways can we extend gamma by A in this way.
What is gamma? Can you tell me?
Any group. Gamma is any group.
No, what is gamma hat?
This is
Same
the
extension.
Aha, just some. Okay. Such that this is exact.
This fact is true for every group or only for Z?
No, this is true for every.
Any abelian, yeah.
If it's central, it must be
Central. I mean, you should know this. You should familiar with yourself with the fact that usually H2 gamma coefficient with an abelian group is a classifying space for all central extensions of gamma by A. And maybe before you proceed, do you know the second cohomology of Z with coefficient in Z?
The wave products?
Hmm?
Wave products? Isn't it wave products?
Okay.
Anyone?
So Z is a free group on one element. So every exact sequence splits, which means that every exact sequence of this form is actually Z times A. There is no other way to extend Z in any other way. So the second cohomology of every free group is trivial.
That would be the algebraic proof. For topologies, I mean, the classifying space of Z is a circle which is one-dimensional. It has no higher cohomologies.
But could you explain again this? Z is a free group, so
Fact, every exact sequence splits.
like
It's a projective model.
it's an exercise.
לא, זה חברה חופשית. אתה רק אומר לאן היוצר הולך.
Yeah, it's basically the destination as a free module. So,
Okay.
so in our case, this is 0, and so the kernel of this map, or the comparison map, is going to be the entire bounded cohomology group. So we have this isomorphism. So now I'm not sure why it's true, but this is isomorphic to R not C S1. I think you can show the same way that this part is exactly R by taking alpha goes into alpha.
I mean, this is something I claimed I did not fully prove. I mean, I gave it as an exercise.
So this is one example where the regular cohomology vanishes, but here we have some S1 suddenly. And now we're going to see an even wilder example for F2.
And just a remark, by the second method, if you take the H bounded of Q is coefficient, the H2 bounded of Q is coefficient in Q, by the same thing, it will be the Adels modulo Q, by what I discussed. So things, really important things pops naturally here.
So now, by the same argument, the regular cohomology vanishes for F2. And so we have this isomorphism. And what we're going to do is build a lot of quasimorphisms from F2 to R. And we're going to do it in the following way. We pick a word W in F2, and we'll define f of W of gamma to be the number of times W appears in gamma minus the number of times W inverse appears in gamma. And so we're close to the break, so maybe I'll give it as an exercise. FW is a homomorphism if and only if W is either the empty word or A plus minus 1 or B plus minus 1. And also FW is not a bounded distance from a homomorphism.
What is FW again? Only the number.
Maybe give an
the
example.
first time or the second time?
AB.
No, the minus.
It's,
The minus.
it's the quasimorphism.
But it is a
Compute
quasimorphism.
FW of AB on S.
Right, but it is a
On a-
quasimorphism, that's what you
Yes.
want to say.
Yes.
That's what he
On a
claims.
normal.
So it's just about,
Usually the it's a non-trivial one.
לא פשוט הוא מחפש פעמים זה מופיע. הוא מחפש כמה פעמים.
מינוס אחד ל-X.
אבל ב-A ו-B זה
לא, אצלנו.
צריך להגיד שזה עם בעיה.
Well, I can't find it long words.
Maybe.
So we have to count how many times AB appears in this. So we have here one AB. Here we have another AB, so we have two. And this is AB.
So then zero.
Yeah,
Minus
that's
zero
fine.
is fine.
גם,
And so we have to take this is a quasimorphism. But this is pretty clear because the only way we mess up this counting is that if we have a start of the word W or W inverse at the end of the first word and then the beginning of the second word is the end of W. And so one can check that
בודק את זה פה, בודק את זה פה, מחבר, עושה תמיד,
that this is bounded.
But it's not bounded.
This is with over. This is you can't with over.
The words you count,
Yes.
you sing, like, you count with over them.
Yes.
Otherwise, it's just one.
It's not bounded. This is from
Right.
you write FW is not a bounded distance.
It's not a bounded distance from a homomorphism. That's the so it's.
It is a bounded. It is a quasimorphism, but it's not in
It's
there.
not trivial.
It's not a
Okay.
homomorphism.
No.
And how do we know it's not a bounded? It's an exercise for the brain.
I can break it.
But this is an example. This is an example Uri said to give.
So you can show that this is in fact an infinite dimensional Banach space. It was first thought that just taking all W's will give you a free basis, but it was not true. But it is still an infinite dimensional space.
When you say this, what do you mean?
What is this space? What's that?
Of all homomorphisms of this type. And then certainly all quasimorphisms are infinite dimensional.
So you mean the vector state generated by?
Yes.
So that's the Cooper example that you said?
This is called the Brooks cycle.
Whoops.
Also the
מצאתי שם.
faculty member at the Technion.
Presentation of the groups.
למה?
This is what you put it comfort.
Okay, so now when we have a bit of a feeling of what's done from us, we usually want to see or show what can we learn from the group, from these groups, and vice versa. These groups, if we know something about gamma. So the first pretty easy one is that if gamma is amenable, then all the bounded cohomology groups are zero. And that may seem as bad news because there are quite a lot of groups. But if we get to it, it was actually very useful when dealing with geometry and things like that, when we don't want the bounded cohomology to see a billion amenable groups. So let's prove this. So we want to show that every cocycle is a coboundary. So we have, now we're going to work again with the gamma invariant functions from gamma k plus 1 because it's going to be easier. So assume gamma is a cocycle and gamma invariant. And we want to find the function phi from gamma k to r, which is also gamma invariant such that call it delta equals f. And we're going to use the fact that gamma is amenable, and so it has a left invariant mean, which is we'll call m from an infinity of gamma to r, and if 1 equals 1, which is a left invariant. And so we define phi as follows. We fix the last k coordinates of f, and we let the first one vary, and so we get a function, and since f was bounded, we get a bounded function, and so we can compute m of this function. And this will define phi for us, and then we just compute what is delta of phi.
As? Could you repeat the definition of phi?
We have k variables that we need to take, and we look at f. We fix the last k coordinates, and we let this vary. So we get a function on one variable from gamma to r, and this function is bounded because f was bounded. So we can apply m to the function along L infinity of gamma to r. And so we just write explicitly what is delta of phi, and we can get the m outside. And by looking at what being a cocycle means, that these types of sums are zero, we get that actually the function here, this is just a sum of functions, is the constant functions which gives the value. F of gamma 0 to gamma k. But now m gives the constant one function 1, and so this is just f of gamma.
How do you see the constant function again?
I don't really want to write delta again. for F.
Okay, but it was the complicated kind of delta, right? It was
No,
the D.
it was actually
or
the
that was
easier
the
one.
easy delta. So, okay, but it.
But you write
Okay.
delta of F, and you take the first summand out of the other ones, and you just get, so you omit this one, and you get gamma of 0 to gamma n, and so this, and all the rest are zeros. So we get the constant function. And then we need to check that phi is gamma invariant. So but f was gamma invariant, and so we can multiply by gamma inverse, but the problem is that we get now gamma inverse here. But now we use the fact that m is also gamma invariant, and now this is a function in one variable which we translated by gamma inverse, and so m of this is just m of this function, which is, and so phi is gamma invariant. And we found a coboundary, that every cycle is actually coboundary.
Just to give a name for the object that we've seen, basically using m, using the invariant mean, we found a function that took f and gave us phi. So it took an element in ck plus 1, and we got an element in ck. Where C is this chain complex. So did any one of us study some algebraic homology and know how to name such functions?
Such functions? The mapping from...
Some specialist functions that take a map, I mean, from, say, a chain complex to itself, that decrease the degree. And commute nicely with, or have nicely behavior with respect to the boundary maps.
Homotopy?
That's an homotopy. So we use averaging on the first variable with respect to m to construct an homotopy, and once we have such an homotopy, that's a general nonsense fact that homology vanishes.
And what about the regular cohomology of an immutable group? Is there anything we can say about it? Now that
it can be pretty much everything.
so it's really special.
Yes.
I don't remember exactly what was C2 from before, but all these zeros says that all the that in an amenable group, all the quasi-morphisms are only homomorphisms plus bounded things. So this C0 is part of C2.
What the values are the reals?
Yes.
Yeah, it
This is
depends.
for real confidence.
Yes.
Right, okay. Here A must be
Yeah,
one.
we showed that the bounded cohomology of Z is S1, so this is not true in Africa. So this is in fact, in some sense, if and only if statement. Johnson showed that if we take all the, if we have a group and all its bounded cohomology groups vanish for every suitable Banach space module R0, then gamma is amenable. So we have this characterization, amenable groups with the bounded cohomology. And so we saw these two extremes of being vanishing or infinite dimensional. And this is in fact what people can say today about most groups. And we show some example. So H2 is infinite dimensional in the following cases. The lattices in rank 1 big groups. In Gromov hyperbolic here's a nice one that I'm going to use later. Best in Fishy Warhammer 2002. If H is a subgroup of the mapping class group of a surface of genus at least 2, not virtually abelian, then its second bounded cohomology is infinite dimensional. And what we have in common in these types of groups is that people construct a lot of quasimorphisms. Somehow the hyperbolicity, which reminds us of F2, is used to construct a lot of quasimorphism, and that's true. This is that the bounded second cohomology is very big, and
are you going to mention the name acylindrically hyperbolic? Something?
I thought so, but then I decided not to.
Okay, very good decision. But it reminds me, there is this notion of acylindrically hyperbolic groups, which is the generalization of many concepts that we've seen, and maybe, I want to put it on in the air here. Someone should talk about it. If you're interested, let me know.
So for higher rank, we don't know, or
We have the opposite inside.
What's the non-elementary group?
Not virtually Z, and
That's okay.
Visually see.
since then it will be 0. That's what I would say. So here's another cool characterization of groups by their second cohomology group. That actually we can characterize from of hyperbolic groups using the second cohomology. So if gamma is finitely generated, then gamma is hyperbolic and non-elementary if and only if the comparison map C2 H is surjective for all Banach gamma modules.
What's the? What's the?
I can't say anything about this result, but it seems very cool that we can describe this hyperbolicity properties using the second cohomology. And another thing which I'm going to use very soon.
Just a question.
Yes.
The lattices, you assume uniform lattices or can you just find it volume?
I think it's true for every lattice.
So,
So this result, suppose we assume gamma is the free group, is there any easy way to see it should be subjective?
If you have the free group,
Yeah.
then what classifying space for the free group? You just make a rows.
Right, you make a rows, and then which is
Then the cohomology of the rows in every higher thing is 0.
right.
So
Okay, so that's
H2
showing,
is 0.
yeah.
Yeah, so
Yeah, okay.
there is a
And with that H, it's an F H2.
So here's
For the free group, it's also for higher ends.
For I higher what?
Right. What do you mean by gamma model?
I don't want to be too precise because like this result is 10 different the following are equivalent of when you take a Banach space on which gamma acts by isometries, or a Hilbert space over C such that gamma acts by whatever. So
finally generated anyway, it's as a group. If it happens to be a ring, it's still as a group. It's nothing to do. Like R is not finitely generated.
right.
Okay.
So if gamma is an irreducible lattice and G is semi-simple with finite center of higher rank, then the second then the comparison map C2 is injected. So in some sense, this is the opposite of the rank 1 case, where we have where we don't have so many quasimorphisms. And now I'm going to combine these two results to show a previously known result, but a very cool one, due to Cohomology and Mazur. If we have an irreducible lattice as above, then and this, every homomorphism from gamma to the mapping cluster of some surface of genus of these two has finite image. So this was proved without a bounded cohomology, but we're going to prove it immediately using these two results. And so this is the kind of results that we see now, where we try to find obstructions to certain kinds of homomorphisms. We take a group which we know has a lot or very few quasimorphisms or a very small bounded cohomology, and we send it to a group with a lot of bounded cohomology, and so the image must be very small or the other way. So here's a proof. We're going to use this and we'll go on. We take such a homomorphism, and so this can be avoided with this theorem by the Margulis normal subgroup theorem. Which tells us that for such lattices, every normal subgroup is either finite or has finite index. So the kernel of this map is a normal subgroup of gamma, so we have that the kernel of gamma is finite, or it's cofinite, which means that the image is finite. So we want to show that the image is finite, so we'll assume that the kernel is finite.
So kernel of P.
Yes. So assume that the image is infinite, so we have a subgroup of, so the image of phi is a subgroup of the mapping cluster. And so by the theorem of Best-Wiener and Fujiwara, we have that every subgroup has a lot of quasimorphisms, which are non-trivial. So we have this queue of quasimorphisms from the image of V to R. But then if we compose it with V, we get a map from gamma to R, which is also a non-trivial quasimorphism. But this cannot be because Bucher and Donald showed that C2 is injective, which means there are no non-trivial quasimorphisms. And so the image is fine.
So you just need to say that it hits a non-elementary subgroup of the mapping class group?
Yes, but it's not virtually abelian because it will factor through the abelianization of gamma, which is infinite. So this is one cool way to use bounded cohomology. And now I want to show some relation to more algebraic properties of gamma.
But you can replace mapping class with a hyperbolic group or?
The problem is that we want every subgroup of.
Yes, it can be virtually.
Yes.
Yes,
The statement is correct with
yes.
with hyperbolic
I know,
but the proof.
Yeah, you have to have so many quasimorphisms that every subgroup has a lot of quasimorphisms. Or you can say that you can characterize the subgroups which have only five, which have small bounded cohomology. Okay, so we say that gamma is perfect if gamma is equal to its commutator, and we say that gamma is uniformly perfect if gamma is equal to its commutator. But also there is some bound on the number of commutators you need to write every group, every element of the group gamma. And
then gamma.
Yeah. And there are a lot of results and conjectures about which groups are uniformly perfect, especially lattices, high rank lattices.
You have an example of a perfect, non-uniformly perfect group. Is there any?
No.
few minutes.
So here's the theorem. Epsilon Z is uniformly perfect for n larger or equal to 3. Was later shown for more general lattices in epsilon R. And now I want to define the stable commutator length of element. Stable commutator length of gamma will be the length of gamma to the n over n. Sorry, the thing is. So this means what is the minimal number of elements in the cup that I need to write in order to write gamma to the n with commutators, and I divide by n, and this always converges because it's a sub-additive sequence. And now our result of Bavard says that the comparison map C2 is injected if and only if the stable commutator length of gamma is 0 for every element of gamma. And so, for example, Bourgeois and Monod showed that the comparison map is injective for all higher rank lattices, so we know that the stable commutator length of all elements of these types of lattices is 0. So we have some relation to a very algebraic property of the group, to the cohomology and the comparison map. And we saw some abstraction results. Now I want to show a very cool rigidity result due to monadal Yuda Shalom.
Excuse me?
Yes.
We don't know that if I have that the z points of some higher rank algebraic group are uniformly perfect in general.
In general, I'm not sure, but
I mean, bounded generation of Carter-Keller is not known in general. I don't know it.
That's a near
No, I think, but in particular, if you take an irreducible lattice in SL2 times SL2, I think it fails. I think that would be.
Okay.
I mean, then it is not even expected.
Okay.
I'm not sure.
so David and Morris showed that these types of lattices of H is not true. You need to take products of some copies of S and R, but these types of lattices, when we take a ring of integers of some extension of the Q, then it's also uniformly perfect. So I don't think it's known more generally than that. Take gamma lattice in G1 times G2, where G1 and G2 are just assumed to be locally compact. And gamma is irreducible in the sense that the projection to each factor is dense. And I assume we have H to be the isometry group of X, where X is a cat -1 space. Then every homomorphism from gamma to H extends to a continuous homomorphism from G to H, possibly after taking factoring out a compact subgroup of H.
G is G1 times G2.
Yes. So we have this very general, but quite a general rigidity result that was proved with bounded methods. And with that, I think I'm gonna move to geometry and how Gromov used this to say things about manifolds, non-positively curved manifolds, master rigidity, and simplicial order. So the claim here is that the bounded cohomology of the manifold can tell us a lot about the geometry that this manifold can support. And I'm going to make that statement exact in a few minutes. But Gromov in his paper from 82 defined it as what's called a simplicial volume. And it's defined as follows. We're going to now look at the regular homology of the manifold M. M is some, let's say, closed manifold. And say C is an H. So this is some cycle which you can write in. These are singulars and simpleces inside our manifold, and it can be written as a finite sum of such with coefficients in R. And we define a norm on this space, the L1 norm, to be the sum of the coefficients. And now we know that over Z we have that for a closed orientable manifold, this is isomorphic to Z. And so we have what is called the fundamental class of this group, which is a cycle which represents the generator of Z. We denote it by.
Maybe you want to take infimum over all.
Which for chain? Define for chain.
Is it for chain or is it?
You take the same definition with that?
So,
You take the same definition with coefficients in that? Or
no, I've done R.
M is n-dimensional?
So,
M is n-dimensional?
yes. And now,
So you're taking the homology class, not the cohomology.
yes. And now the simplicial volume of M is going to be defined as the infimum over C, where C is a fundamental class. And people like to say that this measures how hard it is to describe M with simplest function.
Let me just repeat because you use the bracket M first for the fundamental class. So you have the fundamental class is a canonical element, or actually canonical up to orientation. If M if you pick an orientation of M, the fundamental class of M is a canonical element in the nth homology, and this element in homology actually can be represented by many, presumably elements, by many chains. Each chain has its weight. It's first norm, and we minimize. I mean, we take the most efficient way to represent it as sum of cycles, and we declare this to be the simplicial volume of M.
So we should assume an orientable manifold?
Yes. And now, in this paper from 1982, Gromov relates this very off-topical definition to the actual Riemannian volume of M in a series of theorems, most importantly under some Ricci curvature.
Maybe just give a simple exercise to show that the simplicial volume of a circle is zero.
It will become even easier in 2 minutes.
Yeah, but maybe it's instructive to do it with no tools.
Yeah.
I mean, maybe you can deduce it later, but.
So under some assumptions, we have that the simplicial volume is bounded by some constant depending on C times the actual Riemannian volume of R. And under almost no assumptions, we have that this is bounded by the minimal volume of M, which is defined as take all Riemannian metrics on M, which with sectional curvature bounded by 1 in absolute value, and find the infimal value of the volume with respect to all these Riemannian metrics. Then the simplicial volume is bounded by this minimal volume, which measures which types of Riemannian metrics can this manifold support in the sense.
This CM?
Some constant dependent on M.
The minimal volume is smaller than the volume, so how can it be that the first has some assumption and the second has no?
I think it might be because here we take only metrics with sectional curvature bounded by 1 in absolute value, and here I'm not sure that's the case, but I need to check that.
Okay. So the constant is independent of the manifold?
Yes.
Okay. And we do the minimum over all Riemannian structure now?
All Riemannian metrics such that the sectional curvature in absolute value is bounded by 1.
Okay.
And now a very important one.
By 1 or by minus?
In absolute value.
In absolute value it's bounded by 1. Yes. I see.
So why Raz said it's the exercise is easy because the circle has volume, minimal volume of the circle is 0, but since you don't know this theorem, you can represent the circle by something which is arbitrarily close to 0.
I was actually looking to the bounded cohomology things we're going to see very soon, but here is a very nice result. If M is negatively curved with a curvature bounded by delta, which is smaller than 0, then we have the other way. The simplicial volume is bounded by some constant. Times this. So we have a way to check if the simplicial volume doesn't vanish, which will be very important for a cohomology later in this paper. And now we connect this to bounded cohomology. So we have these fundamental classes in homology.
Sorry, I was distracted. Delta now is bound on sectional curvature?
Yes. And now we are going to
Everything absolute value of delta to the n over 2.
I mean, it's minus delta.
And if M is hyperbolic, then this can be computed explicitly by, okay, not so explicitly, where Vn is the supramal value of the volume of here there's an n simplex in the hyperbolic manifold, hyperbolic space, which was shown to be finite by Thurston in 78. And now we connect this notion to bounded cohomology. So assume we have alpha in the homology.
Can you put on the board definition of Vn? You said it, but...
So in particular, the simplicial volume is the volume. So
and Vn is natural normalization.
So now assume alpha is an element here.
Maybe I'll just say a word about Vn in that hyperbolic space. I mean, do you know what V2 is? The maximal, the supramal volume of a triangle in a hyperbolic space? Pi, and it's actually obtained not for an actual triangle, but for an ideal triangle. So if you have ideal triangles in a hyperbolic space, and they are all alike, because SL2 acts retransitively on the boundary, then can you make a picture? An ideal triangle.
It's a version of
Triangle, and okay, good one. And in 3 space also, I mean, whenever you have an ideal tetraeder, then you can enlarge it somehow by pulling the edges, the vertices to infinity. So whenever you have a tetraeder, I mean, the supermove volume of tetraeders will actually be obtained on ideal ones, because it's always beneficial to pull the vertices to infinity. But actually now the action of SO31 on the boundary is not anymore 4 transitive, and we have different ideal triangles, different up to isometries, and the supermal ones with respect to volume will be the regular ones. The ones like in this picture, but in the 4-dimensional, in the 3-dimensional analog, or higher dimensional. These are called the regular ideal sequences, and it's a non-trivial task to compute their volumes.
And isn't just a negative the curved section curvature? It's not hyperbolic. Doesn't mean that.
Yeah, hyperbolic has constant.
Constant. And what does it mean by? Oh, it's been changed. Okay. It's just bounded by that.
Yeah. So we have an element of the homology of M, which represents a fundamental class, and we have beta in the cohomology, which is dual to H, to A alpha. We have a pairing of homology and cohomology, and we have the beta of alpha. It's 1, and this is by duality. We get that 1 is equal to the product of the L infinity norm of beta times the L1 norm of alpha, but the L1 norm of alpha was defined to be the simplicial volume of X. So we get that 1 over the L infinity norm of beta is equal to X. And so we get that the simplicial volume of a manifold vanishes or doesn't vanish only if beta is in the bounded cohomology of the group. And so of the fundamental groups of M, or of the manifold M. And so we can get a nice result about the fact that if we have such a... So, okay, let me repeat that. Beta is in the image of the comparison map. If and only if the simplicial volume of X does not vanish. Which tells us things about the minimal volume or the volume of M. And so if we know that the comparison map is surjective, for example, then we know that the simplicial volume does not vanish. For example, if the fundamental group of our manifold is Gromov hyperbolic, or any other group that we saw has a surjective comparison map. And why this was very useful for Gromov is that he showed that the simplicial volume is a homotopy invariant, but it's defined in a very
Once again, what is the relation between X and M?
X. I just wrote in my notes X here instead of M, but it's the same.
the relation is equality.
Yeah. And so what was crucial for Gromov in the proof of master rigidity is that if I have two manifolds which are homotopy equivalent, then their simplicial volume is the same. And this is a very elegant way to show that because we define it in a very homotopical way. And so if we relate it to the volume of M, then two manifolds which are homotopic have the same simplicial volume and thus the same volume. And I wanted to show a fake proof of the master rigidity, but we don't have time, so maybe I'll show a real proof next time.
In a special case.
Yes.
Let me. That is excellent. Just add a word about what we've seen here in the last piece is some relation between this bounded cohomology, which is some homology, some L-infinity cohomology theory, with some L1 homology theory, right? I mean, we didn't discuss this, Raz didn't discuss this aspect really, only briefly. He gave us the simplicial volume of manifold, which was some homology class given with some L1 norm. So actually, you can think of it as an element in larger scale theory, which is of L1 homology, and bounded cohomology or L-infinity cohomology is its dual. So, and study these relations is actually what gives you some very nice information. And of course, it's reminiscence of what we know from analysis, the duality of L1 and L-infinity, and you can speculate about LP and LQ, and in particular about the self-dual in-between space, which is the Hilbert space, L2, and one can then study homology and cohomology over L2, which give you L2 cohomology, right, to homology, which is another slightly different flavor, but similar in many senses theory, which we should also discuss. So, that's really excellent.